We are going to start off with example 11.3. It states the Curiosity rover shown in this figure was deployed on Mars on August 6, 2012. The wheels of the rover have a radius of 25 centimeters. Suppose astronauts arrive on Mars in the year 2050 and find the now inoperative Curiosity on the side of a basin. While they are dismantling the rover, an astronaut accidentally loses a grip on one of the wheels, which rolls without slipping down into the bottom of the basin, 25 meters below. If the wheel has a mass of 5 kilograms, what is its velocity at the bottom of the basin? Okay, so we will need to use the idea that we just learned about conservation of mechanical energy in rolling motion. Okay, and so we should have that the energy at the top of the basin, we'll say T, should equal the energy at the bottom of the basin, B. Okay, so at the top of the basin, let's look at this equation. We don't have any motion at first. Okay, so we don't have any velocity to start with, and therefore no angular velocity as well. So we just have potential energy at the top here. So we should have mgh, and this is at the top. At the bottom of the basin, we will have this kinetic energy because we will have some velocity. Okay, so we'll have 1/2 mv center mass squared plus 1/2 I center mass omega squared. Check that's right. Okay. Now at the bottom of the basin, we will have a height of 0 meters, so we won't have any potential energy. Okay, so this is going to be our setup. Now, we're looking at the velocity at the bottom of the basin. So we need to find a way to look at this in only terms of linear motion. Okay, so I put a couple formulas up here at the top so that I can plug in here. So for a point, we have I is equal to mr squared, okay, and omega is going to be equal to v center of mass divided by r. Okay, so let's go ahead and plug those in. So we have mgh is equal to 1/2 mv center mass squared plus 1/2 I, which is going to be mr squared, times omega squared, which is v center mass squared, over r squared. Okay, so we'll have the r squareds cancel, and so we can add these together and we get mv center mass squared, since 1/2 plus 1/2 equals 1. Okay, so now we have this mv squared is equal to mgh. Okay, so our masses will cancel, and we'll get v center mass is equal to gh, and this would be square rooted. Okay, now we can go ahead and plug those values in. G is 9.8 meters per second squared. H is 25 meters, and I don't have a calculator on me, but if we go to the textbook, oh, and the acceleration of gravity of Mars is less than that. I think it's 1/6 of that, or is it 1/3? I can't remember. So this should be Mars. Okay, so this should actually be, let's go ahead and get it from the textbook, 3.71. Forgot we were on Mars for a second. Okay. And so then plugging that into your calculator, and I don't have my calculator on me, so we get 9.63 meters per second. Whoops. Oh, okay. I don't know what I did. Okay, so we get 9.63 meters per second. Okay, and this is our velocity at the bottom of the basin. All right. Let me see if I can turn that off and show. Keep. Okay. Sorry about that. Black. Okay. So now let's look at angular momentum of a single particle, and this will be seemingly simpler. Okay. The angular momentum L bar of a particle is defined as the cross product of R and P and is perpendicular to the plane connecting R and P. Okay, so we have our XYZ plane here, okay, and we have our R vector here and our momentum vector, okay. So if we do R cross P, we'll get L in this direction, okay. Okay. Yeah, so another way to put this is that L, or angular momentum, is equal to RP sine theta, okay, or R perpendicular MV. And R perpendicular is just R sine theta. Okay, that's what R perpendicular means. Now, the derivative of angular momentum with respect to t is the summation of the torque. Okay, so we can go ahead and put this into context. So this is example 11.4. It states a meteor enters Earth's atmosphere and is observed by someone on the ground before it burns up in the atmosphere. The vector r bar is equal to 25 kilometers I hat plus 25 kilometers j hat. Gives the position of the meteor with respect to the observer. At the instant the observer sees the meteor, it has a linear momentum p is equal to 15 kilograms times negative 2.0 kilometers per second, j hat, and is accelerating at a constant 2.0 meters per second squared in the negative j hat direction along its path, which for our purposes can be taken as a straight line. What is the angular momentum of the meteor about the origin, which is at the location of the observer? Okay, so angular momentum, again, let me go back. L is equal to R cross P. Okay, so we can take the cross product, which wouldn't be too bad. Or we can, what else can we do? We can take the magnitudes R, P, and sine theta. Okay, where theta is going to be this this angle between them. Yeah, the angle between R and P. Whoops. So I would suggest probably just taking the cross product. Yeah, I think that would be the easiest way to do it. So we have, let me see if we have enough space. Okay. We have I hat, j hat, and k hat. We have 25, 25, and 0. And 0, 0, and negative 2 times 15 is going to be negative 30. Okay, and we'll watch out for all of our units. Okay, sorry, it's a little crooked. So we have I hat times 25 times 0 is 0, minus 0 times negative 30, which is 0, minus j hat, which is going to be, again, times 0, plus k hat, which makes sense. It should be in a different direction, or perpendicular to the other two. And this will be negative 25 times 30 minus 0. Okay, and again, I don't have my calculator on me. I could probably use this. So, negative, 25 times 30, 750. Okay, and this is going to be, let's see, in kilometers squared, kilograms per second. It's kind of a weird way to put it. Okay, now need to make sure if this makes sense. Angular momentum of the meteor. Okay, this is a k hat. Oops. Alright, so now we can look at the torque on the meteor about the origin. Okay, so let's go here. And remember that the torque is going to be equal to the derivative with respect to time of the angular momentum. So we should have torque is equal to d dt of L. Okay, so right now we have L in terms of just looking at it at one spot, but we need to look at our momentum and our velocity so that we can find the torque about the origin. So let's see. We have our, I'm going to write up here, velocity is typically equal to our v naught plus at, right? This is from our kinematic equations way back when. Okay, now we can write this as negative 2 kilometers per second, j hat, because this term here is our velocity, our initial velocity. Okay, plus a, which is our acceleration here, and this is also negative 2 meters per second squared in the j hat direction, times t. Okay, so this is our velocity, more specifically in the y direction. Okay, and so if we take the derivative of this, we get this component here, or our acceleration. So let's see. Let me see. Okay, so this is going to be part of our momentum. So, momentum is equal to m times v. So this would be our v component here. Okay, so this we'd plug into here, and we will determine our torque by taking our derivative with respect to t of our angular momentum here.